area, and Rob Jacker has arrived, so his 2 talks will be in this afternoon.
Okay. Good morning. We'll be to finish and conclude the random first order, and then the second half, I hope, will be about length scale. So let me just recap what where I arrived yesterday. So we arrived to this construction, which is called the mosaic state, or that I call a microphase separation with many phases. So in which, the supercooled liquid close to the Kaufman temperature, Tk, at which the configurational entropy goes to 0, which one can think that is divided, so in patches, alpha 1, alpha 2, alpha 3. So this is just a sketch of one configuration. And these are, let's say, local phase in which the system can be. And so we arrived to this just looking to the partition function of a frozen cavity, so freezing the boundary, freezing the configuration outside the cavity, an equilibrium configuration, and redoing the thermodynamics inside the cavity. So if you remember, we had, when we did this computation, we had 2 terms. So one, which corresponds to the fact that inside the cavity, I can put a phase which is different from the one which is outside. And this gives you this term, which is the number of states in which the system can go, times a factor which is a penalty, a loss term, which just say that this, it's unfavorable to put the system in another state. We are going to lose some part of free energy. And then there is the other possibility to put exactly the same phase inside the cavity that there is outside the cavity. In this case, this corresponds to the one which is here. So there were questions about whether I should take the maximum, what I should take to compute the length psi, the characteristic length psi, so the characteristic length of the mosaic. So what I did actually was just to look when this term becomes equal to 1. And the idea is just that when it becomes equal to 1, if you just take a length which is slightly larger than the characteristic length when this is equal to 1, then there will be an overwhelming probability to go to other states. And when this is just, R is just slightly smaller than psi, this will be extremely small, much smaller than 1, and so there will be an overwhelming probability to be in the same state than there is outside. So with this, we got this length, this characteristic length. This length, we know that it increases when the configurational entropy decreases, and actually, if the configurational entropy goes to 0, then this length would diverge. And so while we had introduced, so D is the special dimension, and we introduced this exponent theta, which was which characterized the loss in free energy that I have when I put a state inside the cavity, which is different from the state outside the cavity. And then to get the time scale, so we say that the time scale will be a macroscopic time scale times an Arrhenius factor with a barrier, and the barrier scale in this way. So scale, it's a kind of activated dynamic scaling, in which there is a prefactor, delta 0, and then the length to some power of psi. Again, just for generality, I just put psi, a general exponent. And so this gives you a time scale which goes in this way, so which is a function of 1 over the configurational entropy, so like you have in Adam-Gibbs. But then here you have a general exponent, which is psi divided d minus theta. So there were some questions about why I just put this exponent. It's just to be general. And of course, I mean, the most, let's say, natural guess for theta is that theta is equal to d minus 1, just by like in usual nucleation. This means that what I pay here is just proportional to the surface. But while something different can happen, is just that, well, for example, in disorder system, it's known that if I have a state alpha outside and I want to put a state inside, so for example, in disorder spin system, then, well, what happens is that there could be an interface which is extremely well optimized, meaning that if I have a disorder state here and there, well, maybe I would like to put the interface in a region in which it's particularly, let's say, less, I mean, I lose very few energy to put the surface here, and so I'm just carefully choosing where I put the surface, so this, well, and so the surface will be high optimized, and so maybe in this way I could get an exponent which is less than d minus 1. So in principle, theta can be less or equal than d minus 1, and then the exponent psi, in principle, can be higher or equal to theta, so the I would say the natural guess is that psi is equal to theta, but it could be different, and again, why it could be larger than that. The idea is that imagine that you have again, with this representation, you have a surface which is is extremely high optimized, and you want to go from here to there, so you want to go from a state gamma to a state gamma prime. And so here we have this surface extremely well optimized to this surface extremely well optimized. Well, but the problem is that to go from here to there, you don't know if you can go through, let's say, barrier which are really extremely well optimized. Maybe you have really to cross a barrier which is much higher than, let's say, the minimum that you get when you put the surface in this way. So, well, if the barrier is not much higher, then you will have psi equal to theta, and otherwise it will be larger or equal to theta. So, well, these are the arguments. And then, well, you will see that actually in the talk by Chiara Camarotta, well, you will find that, well, there is, well, even if there are these theoretical arguments, when you look at numerics, it seems that things are completely different. Okay, so this is just the summary. So maybe I can say also something else is, when I start the discussion about this, I said that it's strange to think about nucleation because all the states have the same free energy. So in a sense, why the system is nucleating? And well, the reason is that this configurational entropy. So what you can think is that in the dynamics, as I told you, so the state alpha 1 is replaced by state alpha 1 prime. So what you have is you have something which nucleates here, and then it grows, and then it decreases, and grows, and then it decreases, and then at a certain point it grows, it arrives until here, and when it arrives here, well, it's just equivalent in terms of free energy to the state alpha 1, and so it will just stay there. And so in this way, you go from alpha 1 to alpha 1 prime, and then you stay there, and then you go to another state. Okay, that's the summary. So now I would like first to tell you what one can do with this theory. So what are the quantitative things that what kind of quantitative things one can do? So there are two types of quantitative results, or let's say let's put it this way, pre and post-diction. And results. So there are one kind of results which are, let's say, static ones. For static ones, I mean, you really want to know the property of the metastable states. So let's say, for an example, let's say that you want to know the shear, the shear modulus as a function of temperature of a supercooled liquid, meaning, well, so on time scale which are less than the time scale on which it flows, or you would like to know what is the value of the configurational entropy as a function of temperature. So this is a static quantity. You have just to count the number of metastable states. Or you want to know the Biwaller factor of the states. So all these kind of things can be computed with the replica method. And I think, well, Marc Mézard should tell you something about this. Replica method for compute properties of metastable states. And so what I can tell you is that, well, I won't tell you anything about how you do the replica method. It's just that it's based on the ideas, of the mean field ideas that I described. And what you can do is you can really do things which are, you have to use approximation, but I would say beyond, well, apart from this approximation, the method is well defined, and you can try to compute as precisely as you can all these quantities. So this is something good. And actually, so this is for supercooled liquids, and this has been also applied to Hart spheres. So Hart spheres, when you increase the density, they have a glass transition. And so you can also compute the property of the, say, metastable state or the amorphous rigid state that you get for Hart spheres. And this has been done by Parisi and Zamponi. And you can find actually very good quantitative properties when you compare with the with numerical simulation. Okay, so this is the first kind of quantitative result that you can get. So now I would say is the shear modulus. Okay, so so now let's say the dynamic ones. So the dynamic ones, unfortunately, are much more. Is too small, or is okay? Okay. So are, let's say, I would say much more hand-waving and much more heuristic. And I will tell you actually what are the predictions, for example. So you have really to start to say, to do some conjectures. And so I will tell you some of the result that has been obtained by Walliness with some conjecture. So what are the conjectures that he used? So what he used is, well, some value of the exponent first, because you have to know the exponent, and theta and psi. And so what he says, theta is equal to psi, which is the most reasonable guess, as I told you. And this is equal to 3/2 in 3 dimensions, okay? And then I won't discuss at all why he finds 3/2, because I think, well, the argument is interesting, but to me it's not completely convincing. So, well, if you want, you can read the original paper. So there is the original Kirkpatrick-Tumerai-Walliness paper, and then there are other papers in which they discuss why theta should be equal to psi should be equal to 3/2. And then the other important thing is, well, I should tell you what, so if you look at the expression that I wrote down there, so there is a upsilon, so which is in the surface tension, and there is a delta 0, which is coming in the expression of the time, of the relaxation time. And so what Walliness says that delta 0 is actually a function of temperature, which is equal to y0, so upsilon, sorry, which is a function of temperature, and this is equal to k, which is a constant, which is more or less equal for all supercooled liquids times the temperature. Again, I will discuss a little bit why there is this evolution with the temperature. So the fact that, well, there is a universal, so the fact there is, the order is, let's say, the order of magnitude is k times t is not completely crazy. It's just that, well, this is the energy scale of the problem. So it's you look at the system at the temperature, which is, let's say, T, meaning the order of Tg or the order of T melting. So the fact that this is for the order of Kt is not crazy. The fact that it decreases with the temperature is quite strange. But let's just see what you get if you with this assumption. Sorry? Sorry, so delta 0 is the one that I described here. So for the barrier, so the barrier goes like a prefactor, delta 0 times the length. And then here, well, here is the same, you get y. Yeah, you can think that it's just a surface tension. So that's why you say delta 0 equal to y. Okay? So y upsilon, sorry. Oh, yeah. Okay, so let me see if I told you everything. Okay, so let's go ahead. So now what happens to the time scale? So if I, can you go down? Okay. So now if I look to the logarithm of the relaxation time divided by the microscopic time, so this is delta 0, and then upsilon t sc to the 1 to the psi d minus theta. And now, well, let's just use what I have here, and then, well, so this exponent will be equal to 1 with the choice that I did, well, with the Walliness choice in 3 dimensions, and then, well, and then what you get here is, which is equal to k squared divided by sc, which is a function of temperature. Okay, it's just because, well, y is equal to kt, so the t and the t goes away, and then there is a t which I forgot. Sorry. So this was all the barrier divided by the temperature, and so delta 0 is kt again, so t and t goes away, so you get k squared divided by sct. Okay, and then I will use, so let me see if I need it. Yeah, I will use just another relation, which is that sc, oh, let's do it this way. So I know that T ds dt, the entropy now, the global entropy, is equal to the specific heat, okay, Cp, this is the thermodynamic relation. So it means that now if I want the expression of the, so close to Tk, there is a part of the entropy that disappears, which is the configurational entropy. So I know that the jump in the specific heat at Tk is just equal to So T, D, S, C, which is now the configurational entropy, is the specific heat jump at Tk, if I just use this. And so now I know how I can write the configurational entropy equals to Tk, so Sc will be just equal to delta Cp times T minus Tk divided by Tk, okay? And so now I can rewrite the expression which is above, which is log of tau alpha divided by tau 0 times, okay, let me see, is k square Tk, T minus Tk, delta Cp. Okay, I hope I got it right. So let's see. Yes. Okay, so now I have all the things that I need to give you the three, let's say, three quantitative prediction. So, which maybe I will write here if it's okay, so that we have the, or maybe that one is better. No, I will use this one. So Tk is the temperature at which the configurational entropy becomes equal to 0. Okay, now if you just use this thing, so you get three predictions. So first prediction, what is the value? Well, you know that at the glass transition temperature, so tau 0 is a microscopic time, let's say, I don't know, picoseconds, okay? So you know that log of tau alpha divided by tau 0 is, well, let's say it's a stupid universal quantity at Tg, just because the glass transition is just defined as, for example, the temperature at which tau alpha is equal to 100 seconds. So, well, this is a quantity which is the same for all supercooled liquids at Tg. And so this means that now, if this is equal to k squared divided by S configuration at Tg, so what you get is that Sc at Tg is a universal quantity. It's the same for all supercooled liquids. Okay, so that's the first. Did I get it right? Yes. That's the first thing. Then the second one is the kind of, well, actually Walliness derived many other predictions. I just give you three to give you an idea of what are the kind of approximation and what you can get. The other thing is that the length, so now the length psi was equal to epsilon divided by T Sc to the power 1 over d minus theta. And then, so this means that this is equal to K Sc at Tg, 1 over d minus theta. So again, this is universal at Tg, so this means that, well, glass formers has all the same length, so the length of the mosaic is the same for all glass former at Tg. So now I'm not putting all the, I'm not doing the computation, but if you put the, all the values, so what Walliness says that this is something like 6 times A, where A is the microscopic length. Okay? More or less. And then, well, the third thing is that now if you look to the to this expression, which is here, log of tau alpha divided by 0 times this. So, well, of course you get the Vogel-Fulcher, but what you get, if you remember, I guess you must have seen this in the first lecture. So you can define a fragility of the liquids, and the fragility is estimated by the prefactor, which is here. So now you get that you have a clear relationship between the fragility of a system and the specific heat jump. Okay. Yes, it's universal. Well, or if you want, well, what he says is that it changes. Well, it's approximately universal, meaning, well, it's almost the same for all liquids. So the other thing is that the fragility D is proportional to 1 over delta Cp. Okay, so that's just to give you an idea of the kind of result that you can get. But of course, there are, well, some very important assumptions to get these results, which are clearly non-trivial. Okay, so, well, this is just to give you an idea of the quantitative prediction. Then I will discuss now I would like to try to discuss more conceptual problem in definition of the mosaic, and also, well, what are the problems in general, and what are the, let's say, the avenue for future research. So I don't know if there are questions here. So it enters from here, because Tg is defined, so you know the tau alpha. So Tg is defined as the temperature at which tau alpha is equal to, let's say, 100 seconds, okay? And so if this is picoseconds, then, well, this is just a number. So this means that if it's true that tau alpha has this expression, since tau alpha Tg is just always 100 seconds, tau 0 is picoseconds, so this means that this is equal for all liquids in a trivial way. This is equal for all liquids at Tg, but this is also equal to this quantity, so this means that Sc at Tg, so the configuration entropy at Tg is the same, should be the same for all liquids at Tg. No, and the kappa is assumed to be universal. I mean, universal, it should be, it's assumed to be independent, approximately independent of the liquid. So it's, well, this is one big assumption. So,
no, just a couple of comments about the stuff on this slide.
Yeah.
Now, regarding the static quantities, I think both in terms of the assumptions and even at the level of detailed calculations, it ends up that the replica method is basically the same. I mean, you're doing exactly the same thing as sort of in the inherent structure methods in practice as well as conceptually. Okay, so I think there's sort of, even though there's a more I think at the level of sort of being able, I mean, at the level of exact calculations, there is a difference. Yes. But when it's applied to liquids, both, like I said, both in terms of what assumptions you have to make so that you can set up the problem, as well as what you do in practice, you're doing exactly the same thing.
Yes, yeah? It's very similar. There is one issue which is conceptual, it's not practical,
right.
Which is that in neuron structure, you assume that, let's say, a quote-unquote state is an energy minimum, and instead in the replica, you always say, well, it's not really an energy minimum, but well, and maybe we can discuss this more.
No, but then when like I said, if you make that distinction in principle, you should do a different computation, which you don't do.
I agree.
So that's now the other point is in the dynamic, you know, like the I mean the 1 over SC prediction is not Adam Gibbs, right?
Yeah, there is a T which is missing.
And I think the Adam Gibbs works better, though I'm not 100% sure. Yeah.
Okay.
And going from there to the Vogel-Fulcher form, you know, you assume that delta Cp is constant. But if you look at the data, it's clear that it can change quite drastically for fragile liquids. But this is sort of, well, you make a bad assumption, which is not, but somehow that's central to this derivation. So can you comment on that?
Well, so actually I guess what you should do instead of, so a good fit of the configuration entropy is something like this, with a constant here, but temperature, T here, not Tk, but T. So this is a good fit. And so in this way, well, what you get here is this expression, but with T here, it's not Tk. So here I was just, well, a bit sketchy. So in principle, the correct expression. So if you want to use an expression of configuration entropy, which is really, well, it's a good fit of the data, it will be a constant times T minus Tk divided by T, and so what you get here is T divided T minus Tk, which is not exactly Vogel-Fulcher. Well, it will be Vogel-Fulcher when you are very close to Tk. I agree. But again, at least to me, I mean, all these assumptions that you do to arrive here are very suspicious. I mean, not that I think there is something hidden, it's just that I really don't know if they are right or if they are wrong. And maybe I can already comment of one of the assumptions, sorry, can you put it down a little bit, which is the fact that delta 0 is equal to upsilon, which is equal to kT, and this is strange. This means that when I decrease the temperature, Well, it's, let's say, the effective surface tension decrease. So well, it is exactly the opposite of what one had thought naturally. So I think what Wallin, what Wallin has said is that what he thinks is that the liquids are, in this regime, are very well approximated by R spheres plus a small correction. And so if you have R spheres plus a small correction, so what gives you this is entropy. And so when you decrease the temperature, this is going to decrease. And then probably we'll get a constant value at 0 temp, well, when you go to very low temperature. But again, it's not that I'm unconvinced. I just tell you what he said. It's not that, yes? So, well, actually, well, the thing is that really, so the model really relates the time scale to the configurational entropy. So the problem is, well, if the configurational entropy goes to 0, then the model predicts a divergence. But if the configurational entropy, let's say at 100 seconds, also will go away from the extrapolation, then it's not a problem. But, well, just what I can tell you. Okay, so yeah, maybe now I would like to switch. Yeah, no.
Sorry, one last.
Yeah.
No, I guess the business of the delta it's coupled somehow with the assumption that goes into the surface tension.
Yes.
R dependence of the surface tension, right?
Yes.
So as you change temperature, what you're looking at is the combined effect of the two, which may end up going in the right direction.
The two? You mean
because so as you go to low temperatures, this prefactor is going down, but the size of the mosaic is getting bigger, so that's also going down. Okay, so never mind. So it's actually so the combined effect is that the surface tension always decreases because the mosaic size is becoming bigger, which means that the surface tension also from that factor is going down as you go to low temperatures.
You mean the surface tension per volume, or because I mean the barrier is increasing?
The barrier is increasing, but between the delta and the assumption about psi being 3 minus 2, which is somehow related
you mean
to the
between d minus 1 and
theta?
Okay, if there is a crossover between d minus 1 and okay.
So both factors are actually going in the direction of the effective surface energy per unit area decreasing with temperature.
You mean decreasing with respect to what you would expect naively, which is a constant time psi d minus 1. Yeah, okay. Yes, so let me just one thing I'm thinking if I want. Okay, no, go ahead. Sorry, I didn't hear. Yeah. Well, that's Walliner's choice. Then it would be a constant, yeah. If you choose delta 0 constant, but not equal to y, epsilon, I agree. But well, again, I mean, yeah, of course you can. If I have no idea. I mean, maybe something that one has to stress is that I would say the research really now is to understand what this surface tension means, what these exponents are, what is delta 0, what is epsilon, and this is really current research, and so it's not very well understood. And well, there will be a seminar about what the value of theta and psi are, and there is also a poster, so it's really ongoing. So I don't know. Okay, so let me just. So now I think I would like to switch to something else, which is, so here these are, let's say, empirical assumptions. And now I would like to, in the first lecture I gave you some, let's say, hand-waving, sloppy argument to tell you what the mosaic idea is. And now I would like to switch and say, let's say that I have, I don't know, the best physicist at hand. He can do any simulation I want and can do any computation I want. What I should ask him to look at to tell me whether if the mosaic is there or not. So this, I think, it's an important question. If I'm not able to even ask the question, then I'm in trouble. And so I will try to ask what are the good questions. And so, well, I will write here. So, okay, the first one, which, let's say, is related to something which will be discussed later, both in the talk of Chiara Camarotta and I think in the lecture by Silvio Franz, which is related to what is called point-to-set length. So we say, okay, the mosaic is this, again, this cartoon with alpha 1, alpha 2, alpha 3. We did this argument with the cavity. And now let's think to do really, so if the mosaic is correct, then let's try to do, in principle, I can do the argument with the cavity in a simulation. So I can really take, let's say, an equilibrium configuration of a liquid, and then I can take a small cavity, freeze all the particles outside the cavity, and redo the thermodynamics inside. So for example, let's say that I do Monte Carlo, and I just do the Monte Carlo simulation inside the cavity with a frozen boundary condition. So what I should find is that, let's say, now if I take the cavity, so this is the size psi, and then I take the small, let's say small cavity, small meaning smaller than this length, so which, let's say I have a cavity here, okay, a small cavity here, or, well, when I increase the radius r, at a certain point I will have a big cavity here, okay, this is, let's say, R1, and this will be R2, okay? Sorry, you don't read it, this is the R1 and this is R2. So what should I find if I do a simulation like this? Well, what I find if I do a simulation like this is that if R is less than psi, then, well, what we say with the cavity computation should work, meaning that, well, I will be typically, if R is less than psi, I will be typically inside one of these phase, and then the boundary conditions which are outside should fix what is inside. So I should get the same state inside. So, of course, how I can see that I get the same state inside? So what I have to do is to compute an overlap. So, which between the, so let's say really, I will tell you what the Gedanken, let's say, experiment is. I take a first configuration, which is an equilibrium configuration. Then I froze all the particles outside one cavity, and I redo the simulation inside. So now I have two kinds of configuration. If I have the first configuration inside the cavity, and then I have all the configuration that I got doing the thermalizing inside the cavity, which in principle are different from the initial configuration. Now I would like to see whether they are very different or actually they are close to the initial configuration. So if it's true that I get again the same state alpha, so what should I get is that the configuration that I get inside after a long thermalization with this boundary condition should be very similar actually to the configuration that I had at the beginning. Instead, if R is large enough, we know that we are going to change state, so the boundary conditions are not able to fix the state inside, and so, well, the thermalized configuration will be completely different from the initial one. So I won't tell you how one can define an overlap, one can, yes? Yeah, no, it's okay.
Independent of the model?
Yeah, I mean, I will also discuss this. It's a theorem if the time scale diverges.
Yeah.
The time scale.
So it will be quantitative rather than the qualitative facts. The test would be a test of the actual numbers, not so much of the principle.
Well, no, I think it will be also, well, I agree that this thing is just, it will be probably true for many models, and especially all models in which the time scale diverge. But then I will couple this with other experiments, and then I should, so from here I get one length. And then I do other experiment, and the length should be the same, so this will be non-trivial. Okay, so now, okay, let's say that I define the overlap, an overlap which depends on the radius r between the initial equilibrium configuration inside the cavity, okay, which is C1, and the equilibrium configuration that I get thermalizing inside the cavity, after a long time, okay? And then I plot this as a function of R. And so what I should get, if the picture is correct, then I should get something which is, let's say, close to 1. 1 means that the configurations are extremely close. And then when I get R, which is close to psi, it goes down, is psi. So this really means that, well, when R is larger than psi, the boundary condition does not fix anymore what is inside. And well, if you do, you can do with the math, well, the computation what we did for the boundary for the frozen cavity, this will be very sharp and will be of the order of psi to the minus d over 2. Okay, so so this is what I should see. And actually, this is interesting. This means really that the system is developing amorphous order. So there are really, you have boundary conditions which are in a disorder configuration, but actually not a random one, a disorder, but a very well chosen one, and this fixes what is inside, even if it's far away, so even when the length psi is large. So this is the first thing, and in principle, you can say, well, you could do it in simulation, and from this, you get the length psi. So this is the first thing that should work. And then the second thing, which I would call, let's say, point to set. So I call this point to set length, and maybe I should say that this is the point to set static length, and I will define a, let's say, point to set dynamic. I don't know if it's a good definition, but I will do it in this way, length, which is exactly the same, but it concerns the time scale. So I do exactly the same experiment. I freeze the boundary condition outside in an equilibrium configuration, but now I look to the relaxation time of the system inside the cavity, okay? So as I always have my cavity with radius r, and here the configuration frozen. And then now I'm computing how the time scale goes as a function of r, okay? Now, what should I expect if the mosaic is right? Well, if r is less than psi, what happens is that I have the boundary condition, then fix me inside one. So let's do it again. I have alpha here, and then I have here inside my cavity. So while I have the boundary condition, then fix me inside the same state alpha. So the relaxation time will be very fast, but because actually the system doesn't have really to relax. It's just frozen inside alpha. So tau of r will be, in principle, will be small. And then I increase r, and then what happens that increasing r, well, the time scale tau of r will increase. And then if all the picture is right, so tau of r should go to the, let's say, tau for the infinite system, which is the one that you measure in, I don't know, in the dynamic calculation function. And the length scale on which you have this crossover should be psi, okay? Because, well, that's what we said. Above psi, the liquid is a simple liquid. So in principle, this will tell you that, so the mechanism that makes you relax and that makes the time scale big is on the length scale psi, which is the same one that I compute here. Now, this is not trivial. I mean, these two lengths, one can construct models, and actually, I don't know if Rob Jack will talk about, but one can construct models, in particular models, spin models, in which actually these two lengths are different. So that's, if they are the same, that's a really a non-trivial result. Sorry? What do you mean different? So how they scale with the t minus tk?
The dynamical length scales like t minus td, the minus 1.
No, but I'm close. Okay, but I'm just discussing everything close to tk. I did not discuss anything close to td. I agree, that's different. Okay, so that's the second point, and then I would say the third point, let's say the smoking gun, if all the three are right, then it should be, the mosaic should be really on the right track. Again, just looking close to tk. Now I would like to do the same thing, again, same cavity, radius r, and let's say that since I have the best physicist, I can tell him to compute the configurational entropy, because he knows how to do it. And so I want to know the configurational entropy of the cavity as a function of r. So if the mosaic is correct, well, I have a state here, alpha. If r is less than psi, well, the state here is exactly the same that is outside. So the configurational entropy of the thermodynamic, well, for the cavity will be 0. I mean, I just in one state. And then I increase r, and I should find again that the configurational entropy goes to the, let's say, configurational entropy of the infinite system, and when this happens, it does happen exactly again on the same scale. So I think if well, maybe things are more difficult than this, but this, at least if one accepts naively the mosaic structure, well, these three things should be correct, close to TK, and one should find the same length. If one finds different lengths, well, then one has to think why they are different and what is wrong. Yes? Sorry, say it again.
So when you define when you're looking at this cavity,
yep.
right? In principle, you do have a large number of configurations other than the ones that are in the state alpha.
Yes.
Right. So is the relaxation time for sampling all of that, or to reach the?
Is the time scale to reach equilibrium? But this other configuration, you're not sampling them because they are much higher in energy because of the boundary condition.
Okay. Okay.
So, actually,
so
yeah.
And similarly, the configuration entropy you're talking about is not is not when you're doing an unconstrained.
No.
So it's very much a constrained problem.
It's important that you have the constraint. Yes.
Okay.
Okay. So well, now I can tell you, of course, well, these are nice things, but actually some of them people have really started to do to study them in simulation. And so the first, so if you can go down, yes, just that one. No, well, yeah, just go down. Well, just yeah, sorry. Okay, go up to the point 1. Okay, so this first one actually has been done in simulation. Has been done actually in 2 different papers, depending on the overlap. And then, I won't discuss it in detail, but so what has been found is actually that indeed you can find the length over this such that this overlap goes to 0 if the radius is larger than this length and is, let's say, is high if the length r is less than psi. But the results actually are quite different from, so first the overlap is not the overlap inside the whole cavity, but is the overlap just in the center. And, but the thing which is really important is actually that, I can write it here, is that what you get in simulation is not a sharp crossover, but it's something, let's say, that at high temperature goes down this way, and then you decrease the temperature, it goes this way, and then let's say, maybe I'm exaggerating a little bit. Well, then you decrease the temperature, and it looks like it becomes maybe a little bit more sharp, but it's still very smooth. So the length, so the important thing is that clearly there is a length which is growing. You forget the boundary condition on a length which is larger and larger, the lower is the temperature. But, well, this is clearly smooth. And so what has been, one possible origin of this is that actually the surface tension, Y, actually is not equal for all states, but actually in principle is the surface tension between state alpha and state beta, and this can fluctuate. And so this may be a possible origin, and I think Chiara will discuss this in her talk. So now, what about point 2? So this has been done, let's say, in one liquid, and now people are starting to do in different liquids, and I think it's very interesting. It should be done in different liquids, in different geometries, and see what one gets. So well, I mean, this is really technical. So let's say one way to see it. So I have, for a given configuration, I have a density field. So I won't really go into the completely technical definition. I have a density field for one configuration. I have another density field for another configuration. And then I will construct a measure that tells me how different they are. So it's just, I can say, I don't know, if it's, I will get something which I call, so at position X, I will say that I have 1 if the density are, let's say, equal up to some value, and then it's 0 otherwise, and then I integrate over X. So that's an example.
So you're talking about the
Yes, I would like to see if there is a nucleation of something or not. Yes?
Yeah, I see why the point one is telling us if there is a coherence length or a correlation length in the system and maybe a mosaic. But it's not telling us anything about the fact that the number of states is exponential in the cavity, right? So you could just have the same picture with just two states in the cavity.
I agree. That's why I think, I mean, this tells you something, but if you don't have the other points, then you cannot conclude. So, yeah.
It's not so surprising that, I mean, in fact, you're right. I mean, the sharp transition you get close to TK in a finite system, and you have this interface that it has with psi to the minus 3/2. And if you don't work close to TK, it is not so surprising that you get curves that are not sharp.
I agree. It could be just, yeah, I agree completely. Okay, and so now, so the point two, well, it's, I think it's an ongoing, so, well, the reference for this is maybe for point one, so there are two references, but they give you the most recent one, and which is, let's see if I get it, is Nature Physics, volume 4, page 77108. And so now the point two, it's an ongoing project, and so Andrea Cavagna talked about this in in Rome in September, and what he said is that, well, indeed, what they find is tau of R is small when R is less than psi, and then it becomes equal to the bulk tau exactly when R is close to psi. So, well, it's not published yet, but it goes in the right direction. And then about point three, there is nothing yet. I hope somebody will do it. Yes? Yes, yes. 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 I don't know. Maybe other people. Well, the other people knows. I don't think nobody have tried to do the constraint vibration in simulation. I don't know if they tried with linear structure. Do you know, Chiara, if they did it? Okay. Okay. Well, yes, I won't talk much about length, but it's okay. It makes it important, yeah. And actually, there is another thing which is interesting, is again, to study the property of the mosaic state, not just take a cavity, but then maybe take a plane and fix the configuration on the other side. And then, for example, there is something that Silvio did, analytically, it's fixing the configuration on two planes and then look inside. Well, so all these things are interesting. Yes. Are different. Well, I think it's in those models, what happens is, so one tells you something about really static configuration, but then it could well be that the dynamics relax because of a rare event, which is not, well, so if you consider the system on the scale psi, let's say a static point length, then it relaxes, but it takes much more time, because actually what makes really relax the system is a rare event, which has nothing to do with what we are doing in the statics. So some rare defects, for example. And so it's different. So the length scale on which the dynamics converge to the bulk is different from the length scale on which the static converges to the bulk. But we can easily plaquette model, for example, plaquette spin model. Rob? Yeah, that would be, yeah. Yes.
Isn't it the opposite that when the tau becomes somewhat infinity, then you take that to be the mosaic length as a function of r? Because that's the length when the inside blob will not relax at all. So you are stuck to the same configuration.
Yeah, well, so it depends what you mean by relax. So what I mean by relax is really...
Let's say calculate any correlation function and then it won't decay at all as a function of time for some r.
Yeah, well...
And I believe that that should be the mosaic length.
Yes, you are right. I mean, my way to say relax is meaning if I take the system and I run a thermodynamic, run a Monte Carlo simulation, I want to wait the time in which it becomes stationary, and the measure is exactly the same than the Boltzmann measure with the frozen boundary condition, which is, you're right, it fixes you in one state, so indeed, it does not relax, that's why I say that it relaxes faster.
No, but in this case, if you put some boundary which is fixed, then it artificially changes the overall dynamics in some sense.
Yes.
So if you take some length which is defined this way, then that will be somewhat big and it will be somewhat huge, I guess. So length scale which is of the order of maybe 10, 15.
Why? Why should be?
Because up to that scale, the boundary effect is still there in the dynamics. So your relaxation time will not be equal to the bulk dynamics without the frozen boundary.
Yeah, I'm not sure I understood. So you mean that this should be different from the one in one? The psi here?
Yeah, the way you define...
Sorry, the psi here should be different from the one in dynamics?
Yes, the way you defined now. But if you define another way where relaxation times become infinity for that length, then I guess that those two numbers will be similar.
Well, I'm not sure I understand. Maybe we can discuss later. Okay. Yeah.
You say that the equilibrium ensemble is localized in that state, then the relaxation is simply exploring that state, and that will be small.
Yes. So, and yeah. Other question, or can I go on?
In that picture, there should be a maximum of the relaxation time corresponding to psi mosaic.
You mean that it goes this way?
Yes.
Well, yeah, probably. I don't know how large is this maximum, if you can really see it, but anyway, I will be more even, I would say even without looking about the form, there should be a crossover length which should be the same. Then one has to discuss what is the form of tau of R, how tau of R behave when R starts. Yeah. Okay, so yeah.
C of R goes from 0 to the infinite size value.
Yeah.
But this is not an effect that's arising from non-extensive.
No, it's arising from the boundary condition. Yes. Yeah, so in principle, you're right. In principle, there should be, in any case, it should be a length, well, it should be over which you start to have, let's say, quote-unquote, well, it's not extensivity, but if it's too small, you don't have really states. It's a trivial effect, but this is not really due to the boundary condition. Okay. Now, well, I will conclude about random first order very quickly, maybe, so I can have some time to talk about lengths. So what is the questions and the, and let's say the direction in which people are going. So of course, Silvio will discuss microscopic computation, which try to put all these things on a firm ground. Then there are, everybody would like to understand what is the surface tension, what are the value of the exponent A times psi, at least getting numerics. And so maybe one point is, which is more conceptual, is what we really mean by a state. And maybe I will not discuss this, just to talk a little bit about lengths. I mean, state, it's always the problem is always that at the first sight, one say, state is just an energy minimum with some vibration around. This is also what you get if you do the free, let's say the free energy landscape. But then if you start to think a little bit, you say, no, it cannot be true because otherwise there are some paradox which arrive. So for example, if I have an energy minimum vibration and I just change two particles here, it doesn't make sense that this is another state from that one. I mean, changing a particle here, it takes, well, in a big system, it happens every time. So somehow the definition of state is something which is subtle. Probably it makes sense to define state only over the length psi. And well, this is something I think that people are thinking about, but I won't enter in this discussion. Okay, well, so if there are no other questions, I will talk about lengths. Okay. So lengths. So as you heard by Ludovic, there is a lot of activity about dynamic correlation length. And now, as you heard in my lectures, there are other lengths. There is this point to sect length, which is a static length. And one can ask, what is the relation between the two? And then there are also other lengths that has been defined. And well, if I have time, I would like to tell you two things. One, that as Harge said, actually, if the time scale diverge, lengths have to diverge. So now, in a sense, even if lengths have not been studied a lot in glasses, let's say, in the far past, and have been studied now, in a sense, it's normal. One could say, well, I know that the time scale increased, so there should be a length that increased, but this is something that had been maybe understood precisely now. And then you have, but then you have to understand what are these lengths and how they compare. And so I would like to discuss first why all the lengths should increase, why lengths should increase if the time scale increase, and then I would like to try to discuss with you what are these lengths and what is the difference between these lengths. And well, if I manage. So, okay, so first, why, if you have, so let's say that you have a time scale will diverge at a finite temperature, okay? And this at t equal to, let's say, tk. Okay, of course, this is just for practical purposes. And then when you do inequality, you can have just that if the time scale is very large, then you can say the length will be at least larger than something. But now I will just take this setting, so the time scale diverge, and I would like to show you that the length scale diverge. And now, while I have, let's say, first sloppy argument, and then I will tell you what one can do more rigorously. And so the sloppy argument is the following. So imagine that indeed the time scale diverge at tk. And imagine is a, let's say, is a proof, well, it's not a proof, it's an argument by contradiction. So imagine that indeed there is no length scale. I mean, there are some length scale. I can define length scale psi, which is the max over all possible length scale that I have in the problem, I'll say psi I. And by definition, if I look the system on scale which are larger than this, well, the system is just independent subsystem. Well, that's what it means. And so if it's true, so if this is finite, so psi is finite, is less than infinite, then I take the system and I can consider it as independent subsystem of size psi. Now, what is the relaxation time of such a system? Then, well, is the relaxation time of one of the blobs of psi psi, which is, this is just by extensivity. If what happens here has no correlation with what happens there, so I have just independent relaxation, so I will have that the relaxation time of the system will be given by the relaxation time over the length psi, okay, over side of length psi. And now, well, if you take a system which has a length, so a length psi, so over a linear length psi, so it means a volume psi to the d, so the relaxation time, well, actually this is not difficult to prove in general. So for example, if you have a stochastic dynamics, it cannot actually be larger than a constant time c to the d. Okay, of course you can find pathological argument, pathological case, but this is the general thing, because such a relaxation time, so of course the temperature here is is in the constant K, but I don't care because I have a transition at a finite temperature, so here I can put the value of K at Tk. And so this just means that actually, if you want to relax the system, you can take all particle and then put it in the other position. You have an extremely large barrier, but the largest barrier that you can have is K like C to the D. So bigger than this is not possible. And so, well, so now you get the result is that you started saying that the time is infinite, goes to infinite at Tk, and then you say that all the lengths are smaller than this length, and then you get here that the relaxation time then should be finite at Tk, so it's not possible. So there should be at least one length with that diverge, okay? Yes? Yeah. Yeah, as I said, I don't need it, actually. It was just for the purpose of the proof. So I agree with you. So it means that I get a bound which is psi should be larger or equal than a constant time log of tau to the power 1 over d. And I don't care whether tau diverge or not. I agree. It was just for, let's say, simplicity. So that's the bound. And so you see, time scale increase. Of course, it depends what is this factor k. If this is very small, then the inequality says nothing. And of course, if the time scale really diverge, we don't care what is the value of k here. At the end, the length scale has to diverge. So, well, this is a sloppy argument, but actually it can be proved in one case, and you know in one case what is the length size. So, okay, there's one case which has been studied by Montanari and Semerjian. So stochastic dynamics and spin models, but probably is true for stochastic dynamics of more general models. And then in that case, you really get this inequality, exactly like this, with 1 over d, and the length here is the point-to-step length that I discussed before. And then another way to get a relation between time and length is exactly what Ludovic discussed. I don't know if you remember. He discussed a relationship between chi4 and chi of t. So he said chi4 should be equal or larger than t squared divided by ct, and then chi t squared, where chi t is the correlation function divided by the temperature to the square. And then, well, if you take, let's say that you take for the correlation function as a function of time and temperature, you take a scaling relation, just to be simple, T over tau divided by the temperature. Then you just take this, you plug it inside this inequality, and then you get that chi4 should be larger or equal than 1t squared divided by ct, then the derivative of log of tau derived by the temperature square, and there is a constant here, which I think is f prime 1 squared. So don't care about the constant. What you get here is that chi4 is larger or equal of this term. So again, if the time scale, let's say, diverge, log of tau is going to diverge. The derivative of log of tau with respect to temperature is going to diverge. And so since chi4 is just the dynamic correlation length to some power, so again, you get that the dynamic correlation length should diverge if the time scale diverge. And well, it should increase if the time scale increase. So again, you get, again, the same result, but now is the dynamic correlation length and not with the point-to-step correlation length. Oh, yes? Well, it's, let's see. I mean, let's see. I think, well, the fact is that the divergent chi4 means really that the dynamic is correlated over long lengths. So, well, all the examples that I can think of, they had some diverging length scale. So maybe you can diverging time scale, sorry. I mean, maybe one way you can have a very, well, soft modes with a very long length. But this again, I mean, a soft mode with a very long length will maybe can give you a divergent chi4, but there will be a kind of divergent relaxation time just because the long. But I don't know. Okay, so this was just to tell you what Jorge said already. If the time scale increase, then the length should increase. And while we have even inequality, and actually this inequality, as Ludovic told you, at least if you do it in simulation, you check it in simulation, actually it works quite well. So, okay. So now I would like to try to discuss what is the difference between all these lengths and maybe cite other lengths. So let's see, maybe I will write them right there. So there is, okay, now it's a list of length. Of course, I will not start to consider all the lengths in the literature. So there is the first one that I described. So it's the point to sec static, okay? Then there is the point to set dynamic. Then there is the one that you get from dynamic heterogeneity, meaning from G4, the one that Ludovic described. And maybe I will actually discuss especially these three, but there are others, so I will just put here a list. So there is, let's say, one that you get if you study finite size scaling. And if you study finite size scaling, it depends also on the quantity that you're looking at. So depending on the quantity, you can get different lengths. And then, well, let's say there is another length, which is the one length that has been introduced by Harge recently, which I won't discuss. Let's just say Harge-Kurchan's length. And then there is many other ones. And then at the end, I will put one which nobody knows how to define, but many people talks about, which is the cooperative length, which actually we don't know even how to define. So maybe it's not a good length. But I mean, if you look in glasses, for example, starting from Adam Gibbs, you say there are cooperative rearranging regions which have a certain length, and there is a length which is the length on which you have cooperative motion, meaning that maybe there is in the dynamics something which is not cooperative, so it's not important to set the time scale, but that you can pick up if you look, I don't know, for example, to dynamical fluctuation. So this is, well, it's something that nobody really knows. Should ask. Well, no, it's not a 2-point. It's a point to set. It's like a.
At the end of the day, it's something like 1 over the complexity. But you don't define it that way. It turns out to be that.
Okay. Okay, now actually I don't know, how much time do I have? I start at 9:07. No, okay. But yeah, but when should I stop? In 15 minutes or not? I mean, it's in 10 minutes. Okay, I will go then fast through the example that I want to discuss. And so the example I want to discuss, which is very, very simple, but which I think is important to understand the difference between the lengths. And then I will do another example. So the example is the following. So now forget everything about glasses, and let's just look at a very simple model, which is a lattice gas. Okay? And let's see what these lengths are in a lattice gas. So a lattice gas, I guess you see it already. So you have particle on a lattice, let's say 2-dimensional lattice, which is not coming, well, okay, it's here. They jump on a lattice in a stochastic way. So it means that the configuration of the system are occupation number. You can have 0 or 1, which correspond to the particle, and then the particle can jump to another side if there is no particle on this side. So you have a stochastic dynamics. So I won't be, let's say, I won't go into the detail just because it's simple and I have no time. So the idea is that at each time step, you take a particle at random and then you try to move it with a certain rate, which I will call 1 over d, and then you try to move it to the neighbor, and you do it if there is no particle on the neighbor. Okay, so this is a lattice gas, and the lattice gas you can prove is a very simple model, meaning that if you look to the thermodynamics is just, I mean, each site are independent, occupied by a particle or not, and so actually, let's say the Gibbs measure, exponential minus beta h, let's say minus mu, or well, plus mu, times the density, times the volume, actually becomes just, well, there is no h actually, and so you just get exponential mu sum over I and I. So the thermodynamics is completely trivial. So if you want to get the partition function, you just do the sum over Ni, which equals 0 and 1 of this. So all the sites are independent. There is no static correlation at all. There is nothing from the statics. No phase transition. All the sites are independent. So of course, well, in this case, if I just start to study the point to set static length, well, there is nothing. All the correlation lengths are let's say 1 or 0. Okay, but let's now look at the dynamics when rho is close to 1. So when I have many, many particles, and so when I have many, many particles, actually I have, the nice thing is to think about the system in terms of vacancies. So meaning that I have a lot of particles, and then sometimes I have a vacancy. And the vacancies are very rare. So a vacancy is just a site which is not occupied. So the density of vacancies is just equal to 1 minus rho. And now you can understand the relaxation of the system in very simple terms. So what is the relaxation? How do I define relaxation? So I define the relaxation time as the time over which the site typically changes state. So if I have a particle here, the relaxation time is the time over which the particle, let's say 1, which is here, jumps, so go away. And so what is the relaxation time? So the way to compute it, well, you can compute it exactly in the limit rho which go to 1, but there is a simple way to get it is, so the time scale over which each site changes state. So how I can compute? So I have the vacancy, and the vacancy goes around, so they do actually a random walk on the lattice. So the number of sites which is visited by the vacancy on a time t is just equal to dt. This is the, so let me explain. So each vacancy make a jump on a time scale which is 1 over d, which is here, and then the number of sites probed by the vacancies is dt. Actually, it's not really dt. There is a log correction, but let's not care. It just runs. So there is a random walk here, and so the number of sites is dt. And then this is for one vacancy. So I have many vacancies. So I have the density of vacancies rho v times the volume. So this is the number of vacancy. And now what I want to find is the time such that, so this is the number of sites visited by all the vacancies. So the vacancies are independent. So I have vacancy here. They start to move like in this way. And then I would like to find the time scale over which typically a particle is visited by a vacancy. So it will relax. So it means that I want to have this, which is equal to rho times v, which is the number of particles. Okay, roughly. That's just a scaling argument. So what you get here is that if you get the time scale, the relaxation time scale goes like 1 over d times rho v. Okay. So when rho close to 1, this is 1 minus rho, so the relaxation time diverges. So you can really think to the problem like you have vacancy, which goes around, another vacancy, which goes around here. And actually, because they do random walk, they are just visiting all the sites here until this length. And when actually they arrive to this length, so you have bubbles everywhere, and all the sites have been visited once. Okay, so now what is, what is chi4 in this case? What is the dynamic correlation? So the dynamic correlation can be computed, but actually you can maybe understand. I don't have much time to describe it in detail, but actually the dynamic correlation length here is given by this length. And the reason is that actually, so what measures the dynamic correlation length is, let's say, or the dynamic correlation volume is all the particles that relax because of the same mechanism. Since they relax because of the same mechanism, they are dynamically correlated. So all the particles which are here, they relax because of the same vacancy which is here, and then they are dynamically correlated. So chi4 is just this volume, okay? And the length is just that length. So chi4 here goes just like 1 over rho. And so here is a clear example where the point to set the static is just 1, and chi4 goes like 1 over rho. And here, actually, if you do the point to set dynamic, actually the point to set dynamic, it goes like the one that I get from dynamic correlation. And the idea is just the following, is that if I take a system, well, when the time scale will be the same one that in the bulk. Well, the problem is that if I take a small system, so the time scale to relax the system, well, I should have a vacancy, and then the vacancy should go around over all sides of the subsystem that I'm considering. And then it's only when I reach a system size in which I have one vacancy, typically one vacancy inside, then I reach the time scale that I have in the infinite system. So, well, this I'm sure is not clear, but sorry? Yes. So tau, so now is the tau as a function of L square, where L is the size of the sub box, also, or let's say R square. So this goes like, so this is 1 over the rho, and this is rho. Well, it's, yeah, 1 over rho vacancy. Okay, so this is the time scale. So the time scale converts to the value on this. So here is a case in which you see that, so the Xi point to set static is different from the Xi dynamic, the dynamic heterogeneity length. They are different. And yeah, in principle it's, and then the Xi point to set static is different from the Xi point to set dynamic, even if, well, there are some subtleties, but it's okay. So, there is a difference. Yeah, the density relaxation is, has another time scale with respect to the particle. So, for example, the diffusion coefficient, so if one can write down the, so the diffusion coefficient for the density does not go to 0, if I remember well, when rho go to 1. It's the self-diffusion coefficient of the particle that goes to 0 when rho goes to 1. So that's a difference. Okay, so, well, now I'm finishing. So, so the other two things that I would like to tell you is give you other example in which the length can be different. So now I would like to give you an example in which the point to set dynamic length will be different from the dynamic heterogeneity length. And the idea is the following. Imagine that, so for example, maybe this is a good representation of what happened to the mosaic relaxation close to TMCT. So imagine that you have some activated relaxation over a certain scale, psi here. But since there are maybe, well, you can think there are soft modes, or actually you can think that there is, so an activated relaxation here, but once I relax here, I create, let's say, an avalanche of relaxation around. Okay? So actually, at the end, the number of particles that relax is larger. Okay? And so all the particles that relax are there, but the microscopic process, so let's say the region over which I really have to have a cooperative motion or have to jump a barrier is this one. So in this case, well, what you can think is that, so if the other process, so the avalanche process is extremely fast, so what you have is that the dynamic correlation length will be this one, CDH, and instead the point to set dynamic, the one that in which, well, if you start to confine the system, well, you confine it, but even if you confine it like this, since this is very fast, you will see that the time scale does not change almost, because what set the time scale is this process. So it's only when you arrive here that you really start to change it to affect the relaxation time, and so the two lengths will be different. Okay, and now I will conclude just telling you, in principle, in the different models, how these lengths should compare. So I think, so let's say we start with random first order, and I don't know if somebody told you about frustration limited domains, maybe Gilles, no? So, okay, well, so forget about frustration limited domains. And so in this case, so in the case of a RFOT, I think, as I told you, the point to set static, in principle, should be equal to the point to set dynamic, just because what sets the relaxation process is the static, it's thought to be this, what you get in the mosaic, so the static constructor of the mosaic. And on the other hand, you can very well have that this is less than the dynamic correlation length, okay? Which just for example, the reason that I explained before. So dynamic correlation length, I think in general, you can think that is larger than the point to sets. And well, we don't know really what's the relation. And then let's see, in kinetically constrained model, that will be discussed by Rob, I think but I may be wrong, that Xi dynamic correlation should be equal to the Xi point to set dynamic, which in general should be much larger than the Xi point to set static. Okay? So, and then let's see, no, I don't have other model that I want to discuss. So you see that there are different lengths, they have different meanings, and maybe measuring them, you can really make the difference between the different theories. So that's also why it's very interesting to look at this length in simulation and understand what theories I have to say about this length. So I will stop here. Thank you.
In complex fluids. So
yes.
what happens in this case when you take and you limit the size that the liquid can sample? Does the time go up, get slower?
So in principle, so two answers. One is, in principle, it gets, so let me see. Well, it depends really on the boundary condition. If I fix the boundary condition in equilibrium configuration, which I know is something that in experiment, of course, you cannot do, then the time scale actually becomes faster, just because the system does not relax, it's ineffectively in a glass state. But then if I take a free boundary condition, so let me think. If I take free boundary condition, I guess probably the time scale should be close to TK, probably should be smaller, but I'm not sure.
Well, okay. I mean, I think it's something worth thinking about because there's a lot of evidence, and it's extremely difficult to get the time scale to get longer.
Yes.
In molecular glasses, not in colloidal glasses. They apparently, when you confine them, they get longer.
Yes.
But in molecular glasses, at least, they tend to go down or stay the same, and you have to really work to make them go up. Yeah.
Yes, yes, I agree. Even if from what I understand, which is not much on this experiment, there is always the issue of chemical, let's say, problem of chemistry with the surface. So depending on the surface, things can be different. So how you confine the system.
But it generally doesn't go up. So
okay, it goes down.
If this predicts it goes up.
So you mean that TG?
In other words, TG would go up as you confine it, and that's not generally what's seen.
Okay, TG will go, okay, well, we can discuss later. So you say in experiment TG goes down?
TG generally stays the same or goes down.
Okay.
Yeah.
Can I go back to Jill and ask, what would then distinguish between exponentially large number and just a few? Like if you have this mosaic picture, but
two states?
Just two states.
Well, I guess the third experiment, the third thing, okay, let's see. The third thing I would say, there will be no configurational entropy in that case. So if I just change the system, I look at the entropy of the system, changing the size with the boundary condition fixed, I should see no change, which would mean that what we call configurational entropy is not the true configurational entropy.
This random first order transition model makes sense if order parameter or local order parameter, which defines this domain, is small in number. In other words, a few order parameters are dominant. Then it makes sense to define domains. But then, in this case, interfacial energy will become very large, right? Because for instance, the examples we know about the whole first order transition is dominated by interface. Entropy cannot overcome that. So in order to reduce this, and also in reality that we see, for instance, we can see icosahedral order developing in liquids and then become frustrated. So we can choose this as, for instance, as a one of the order parameter like that. But in reality, there are so many things happening in the system, right? There are so many order parameters and overlapping order parameters in the words that Xi may not be defined by one kind of correlations, all different kind of correlations. So if you enumerate this number of order parameters to define domains, does the theory still survive?
Well, I'm not sure I understand. I mean, the other parameter, I think So you can have many, many different phases. So in a sense, you have, well, quote unquote, order parameter for each one of the phases. So you have a field that you can put for each one of the phases. So that's...
Inside the domain, there may be many overlapping order parameters.
Yeah, it could be that, well, and then the theory wouldn't be correct. I mean, if many, you mean many 10 or many exponential in the size of the system? You mean what, the two? The exponential in the size of the system or many?
A power law number of power law size.
Well, it's the power law size of the system. Well, it's what happened in this case at low temperature. So I don't know. Well, I don't know.
Okay, let's come back at 5 to 11 and then go to the second talk. Thank you.